So if you take a flash drive that people are familiar with, sort of on the order of a sugar cube or something, and if you made that out of DNA, it would hold an exabyte of data.
Data. It's kind of what we're all here for, right? At the end of the day, processing and storing data is the cornerstone of the modern industrialized world. But the way we deal with that data is changing at an astronomical pace. Supercomputers, HPC, AI, they are all changing our relationship with how we store and use data. And testing whether our current suite of technology, such as RAM, hard drives, and SSDs, are up to the task. So in this episode, we'll be looking at how far we've come since the early days of computing and how that's influencing where we look for future technological advances.
You're listening to Technology Untangled, a show which looks at the rapid evolution of technology and unravels the way it's changing our world. We're your hosts, Michael Bird
and Aubrey Lovell.
We always like to start with some statistics, and the ones around data are particularly impressive. So here we go. The total amount of data generated by humans is growing extremely quickly. According to the market research firm Statista, in 2023, we generated 120 zettabytes, with a Z, up from 97 zettabytes in 2022. In 2024, it's likely to be around, get this, 147 zettabytes and 181 zettabytes by 2025. That's a lot of growth. And with the explosion in generative AI, the real number might be even higher.
In terms of the actual storage, the numbers are just as impressive. In a follow-up report, Statista claimed that 2.6 billion data storage units have been sold in recent years. However, that's fallen from over 3 billion in 2014 due to the explosion in cloud storage.
The headline is, there is a lot to be stored, and for organizations, the demand is growing exponentially. Patrick Osborne is a Hewlett Packard Enterprise Senior Vice President and Head of the Storage Division.
Storage doubles, triples, quadruples for our customers every year.
Yeah.
So for example, we had a big customer advisory board yesterday, and one of the key growth areas was many of our customers are experiencing 20 to 40% growth in their on-prem Kubernetes environment.
Wow.
Right? If you think about machine learning, if you think about certainly generative AI, it's all about the data models. And the more data you have, you can create more accurate models, and you can, certainly affect your business in a positive way. So for us, storage is always growing.
And if you want to know more about Kubernetes, you'll find a link to the episode we did on that in the show notes. It's amazing to hear the demand for storage is growing that quickly, but it's not surprising. As we outlined in the introduction, the numbers around our data are absolutely staggering.
But that information doesn't just need storing. At some point, it all needs processing. And processing requires compute, and compute requires memory. Quick access storage that can be tapped into to pull and push data through CPUs and GPUs. The thing is, just adding more memory to a system adds cost, complexity, and uses a lot more electricity.
Hi, my name is Aidong Xu. I'm the Head of Semiconductor Capability in Cambridge Consultant. The major trend is actually driven by the market demand in particularly IoT, AI, or HPC. Artificial intelligence, is all about data crunch. One of the key pieces of jigsaw within this whole computing system is memory. Memory not being paid same attention as the processing, but people now do realize this is a key technology. It can be a bottleneck with the current mainstream of memory technology based on transistor switching. And those are being discharged, which is all the energy will be wasted every time you discharge it. So I would say the headline really is to say we need a memory device, power efficient, much lower power than current technology, and a much high speed because so much data required to store these days.
So we have ever-increasing demand for storage and compute power, and memory technology which sits in the middle of it and is starting to reach the limits of its economical viability. So what comes next? Well, believe it or not, the IT world wasn't always driven by RAM and spinning platters. In fact, to get a look at what the future of storage might look like, we have to ask a historian. Trust us on this one.
I'm Colin Eby. I am a volunteer at the National Museum of Computing, and I concentrate on representing actually the Hewlett Packard collection. Well, the National Museum of Computing is this fantastic collection of machines and education programs and galleries and outreach that's based in Bletchley. It has probably the best collections that you're going to find, especially in Europe.
Colin is an expert on where we've come from in terms of computer storage, which is a very, very long way, and started off with what we now know as separate memory and storage as one technology with one purpose: to store basic signals that can be passed through the computer.
The simplest is what you use for a register or an accumulator in a system, a stable device or circuit that held just an on or an off and would hold that as long as you had power on it. The problem with this, of course, is it's physically large. It's the size of a couple of fingers worth of space. It's not practical for doing, kilobytes. So how do you do that? Well, mercury delay lines are a particularly fascinating mechanism. It basically relies on the stable and slightly higher than in air speed of sound waves through a bath of mercury. And basically all that's happening is you've got effectively a speaker in one end and a microphone in the other. And so for as long as that goes round and round in a circle, you have a pattern representing data that's stored in memory. On the other hand, if you look at the Williams tube, it's literally using an old-fashioned CRT and drawing dots across the screen of a CRT. But these are interesting in that their RAM is randomly addressable, unlike the mercury delay line where you sort of have to wait until it comes by again. Here you can pick whatever bit you want off the screen. So this is a lot faster.
Can you talk to me about the Decatron?
They're a counting device where you've got a whole bunch of little wires that light up inside of a neon gas. They nudge the charge from one wire to another. And if you can count off how many times you have to nudge it, you can figure out what potential value is there. Now, this is interesting in that it's not a binary storage device. It's not storing ones and zeros. It's storing, as the name suggests, a digit from 0 to 9. They're so reliable, relatively speaking, that they can be 60 and 70 years old and still work.
It's funny Colin mentioned optical memory with light changes because that's actually a technology which might be coming back around. In fact, you'll notice that a lot in this episode. There's an old Mark Twain quote: "History doesn't repeat itself, but it often rhymes." A lot of the technologies that were being experimented with in the bold new world of the 50s, 60s and 70s might seem a little odd to us today, but they might not have been quite so out there as we think. Here's Aidong.
There are half a dozen different technology are being developed over quite a lot number of years now, over a decade even some technology. One of the strands is actually called the optical phase change memory, using the light signal as a media for memory device. A switching light is actually the energy consumption is better than the switching electrical transistor, if you like. The energy consumption is very low, and it's not conceptually it's not new. I think that people already do in the lab. If we're talking about in the time horizon of decade, I think the optical memory will become a major player. It's definitely something to watch for.
So it seems that technology which was being experimented with in the early days of computing could be due a resurgence. Now, it would be horribly oversimplifying it to say that there's any real similarity between a Decatron and optical phase change memory, which is the most sci-fi sentence I've said in a while. Nevertheless, the idea of using light for rapid memory access rather than transistors is absolutely fascinating.
And experiments in new ways of doing things couldn't come at a better time. Patrick agrees that there's a bottleneck in the fabric technology, essentially the storage side of things and how it scales.
We're certainly moving towards mostly deploying storage on NAND technology, right? Okay. So NVMe, SSDs, and whatnot. And so finding new ways to provide, new packaging, new density. Certainly, I think one of the areas is that when you design systems, right, the bottleneck moves, right?
Yeah.
So for some time it was the CPU technology, for some time it was the actual media, and now we're actually moving into some of the fabric technology. So having fabrics that allow you to have throughput, scale, moving from 2-node configurations to tens of nodes to now thousands of nodes in a storage configuration. Very interesting.
So what's the answer? Well, there's still plenty of space to make bigger computers.
But that doesn't solve the throughput problem or the rising financial and environmental costs of running these systems, which we explored earlier in this series of Technology Untangled. You'll find a link to that episode in the show notes. A better technology might be what's needed, but what? And how far away could we be to adopting a whole new approach to storage and memory? Here's Aidong.
I think it's something going to be changed quite a lot within the next 5 years. Leading the pack is a resistive RAM or RRAM, or some people call it ReRAM. Basically, it's a resistive RAM. Based on the principle, you apply the voltage and it will change the resistance of the material depending on the voltage applied. In a semi-physical size, it can make a much higher density memory storage, so that imply a lower cost. So this make a really headway. I think within the 5 years, we think the resistive RAM probably occupies 60 to 70% of market share. Another interesting technology is a magnetic type of memory device. So it's based on the magnetic field principle. So there's one particular technology people call the STT-MRAM. The STT stands for the spin transfer torque in a magnetoram. Basically change the direction when the electrons spin. It changes the property, changes the conductivity. We can use a magnetic field to influence that electron spin. As I said, it's based on magnetic field, so you have really low power consumption and also potentially very fast.
Fast, cheap to build, cheap to run, high density. There seems to be a lot of options ticking a lot of boxes for new memory tech on the horizon. But again, are they actually new ideas or old ideas revisited? Well, they're sort of both. It's the whole history rhyming thing again, especially when it comes to magnetic memory.
So core memory-based computers, which core memory is basically a lot of little magnetic donuts that have been woven together in this fabric. It's a fabulous technology based on just switching the magnetic pole of this little toroid, this little magnetic donut. And they got them pretty small by the time they started being phased out in the 1970s. You can get multiple kilobytes and up to megabytes in these panels of memory. But it wasn't practical because it's expensive to make. And by about 1971, 72, you start to have these early RAM chips, which can be made for much smaller amounts of money.
Okay, so you've got your memory on point, be that optical, magnetic, or spin torque. That's a bottleneck out of the way. But is that the most efficient your system can be?
Well, no. The memory still has to get the data from the storage to the compute, then pull the computations back out again for further analysis or transfer back to storage. It does that very effectively, but as we get into the realms of exascale compute and AI-optimized HPC, all that movement from one piece of hardware to another slows things down. It also uses electricity and generates heat that has to go somewhere. That's especially important in large language model-based AI, where training and inference requires a lot of data to be prepared before it can be processed. It's a major burden on a system to get everything where it needs to be for training or simulation to begin.
So how about you just make it all one piece of technology? What if, say, you make the CPU, GPU storage, and memory one perfectly optimized thing?
Well, that's something HPE has been looking into. Here's Patrick.
So first of all, there's the concept of data preparation, right? So you have to have a data lake and prepare that data and understand about it. So that's a lot of processing in its own. So you have to be able to understand what you have, tag it, put it into vector databases and whatnot. And then there's the challenge of being able to feed the GPUs that are doing the modeling, tuning, the inferencing. So that's a lot of throughput, right? And you have to be able to very quickly recall that data and get that as close to the GPU as possible. And then if you think into the future, designing systems that actually co-locate your data with the GPUs is going to be, I think, a new paradigm going forward, where you have things like DPUs, GPUs, some of the new CPU technology co-resident with the storage itself.
And so the big challenges that we're maybe trying to tackle at the moment is how can we connect everything together as quickly as possible? Because with AI technology, the demands for getting that information into those GPUs as quickly as possible. Is that what we're talking about at the moment?
Yeah, absolutely. And you have to think about the systemsness of it as well too, right? It takes an ecosystem. You have to have not only the data and the models available, you have to have all the infrastructure to go with it, and all of the new sort of open source tooling and applications and Kubernetes and the whole thing that comes along with it, right? It's a system and it needs to be treated as such.
Maybe 10, 15 years ago, it did feel like everything was sort of siloed. You had your storage and your compute and your networking, and they were connected together. But are we saying nowadays everything has to work so much more seamlessly together because everything is happening so much faster?
Yeah, absolutely. And it's a pipeline.
That could be a game changer for cost and efficiency. And there's more. There's another type of memory we've touched on, but not really explored yet, which could be the perfect candidate for any new unified computer systems. Here's Aidong.
There's a technique we actually use here in Cambridge Consultant. We try to make a different architecture, which will let you to access to memory in a very different way. In the conventional computation, you have those sort of sequential operation. You fetch the data, you do the computation, then you store the data. Now, the much more efficient way is you compute and store it together. By doing that, you are much more efficient. And at the moment, people really like the phase-changing memory technology, which have a good potential for this particular trend called in-memory computing. So the phase-changing memory is basically the data stored using electrical resistance, contrast between high conductivity crystalline phase and the low conductivity. So when you phase change, you have the conductivity change. Now, this technology is very, very interesting because it has a promise of low power, the read and write, and also offer the very good high-speed operation.
Crystalline memory. Wow, the future is now, and it's pretty cool. Of course, combining storage and compute into one united piece is great for efficiency. It means your smart technology or IoT devices can be smaller, cheaper, and more efficient. And on the other end of the scale, it makes supercomputers that much more powerful and efficient, being able to process everything with the minimum of distance to cover between data and compute.
But there's a completely different angle too, and one which is important to many organizations. Because for many people, actually having the flexibility of a very open system is much more important than the speed of a closed one. For example, a system where you can scale up and down what you need or have the data or compute available to different parts of the system as and when you need them. Here's Patrick.
So one of the things that we've been working on is the concept of this disaggregated architecture, so separating your compute and your density and be able to scale that number of ways. I'd say the cloud operational model is very interesting for customers. They want storage and data management as a service. They don't want storage arrays, right? So being able to have a set of workloads and performance levels that we manage through GreenLake Cloud Platform and have that very, very easy experience so that we take care of the infrastructure and the developers and data architects can go do their job, right? It's very important. And then being able to integrate that into, when we think about our offerings around private cloud, right, AI native stacks, less people are buying just along horizontal lines, like just give me a storage architecture. They really want a vertical slice. I want to run this workload in the stack. So you're thinking about a high level of parallelization. Sure. So millions, if not hundreds of millions, if not billions of files, right, being worked on by tens of thousands of applications running on a very distributed architecture, right? And so for our customers to be able to take what they have in a traditional storage sense and be able to move into that model is a brand new way of designing systems and application development. So it's a very exciting opportunity.
But all of this covers the art of dealing with data at incredible speed and processing it immediately. Sometimes that's on one unified chip. Sometimes it's across parts of a system separated and called upon when needed. But what if you don't want that at all? What if you just want your data to sit there, archived, forever?
Well, there's a solution for that too. And it could be right at your fingertips or on the tip of your tongue, literally. Here's Aidong again with just a snippet from our conversation that sent us down a rabbit hole of discovery.
We actually did a project. It's using DNA as a data storage. It can store so much data within small size. So essentially, it's the density that's unmatched by any technology today. So if you're looking for vast amount of data storage and without the power consumption, without the space, and then the DNA storage is another fascinating technology to watch for.
It was a fleeting moment of our conversation, but it got us thinking. So we tracked down someone to tell us a little bit more about DNA storage, a biological engineer who is actually making it a reality.
My name is Mark Bata. I'm a biological engineer at MIT. So nature has been using DNA as a storage medium for information, genomic information that is, for 3.5 billion years. It's nature's tape drive. So what is it? It's a sequence of letters, A's, T's, G's, and C's, 4 letters. With DNA, you can store information in that sequence. We can just think of A's and T's as zeros and G's and C's as ones.
What sort of storage density are we talking about here?
So if you take a flash drive that people are familiar with, sort of on the order of a sugar cube or something, if you made that out of DNA, it would hold an exabyte of data.
Why can't I go to my local shop and buy a DNA flash drive?
Yeah, well, nature certainly took that as a no-brainer and did it, right? The reality is that we haven't had the research and development investment yet to develop technologies around writing and reading and accessing DNA as a storage medium for our digital data purposes. Let's say it's an image of a cat. You have to convert that image of a cat into the zeros and ones, and then take those zeros and ones and convert them into this ATGC bit stream, which is a very standard and simple process. But then you have to actually make the DNA. You have to synthesize it. So once the DNA is written, though, then how do you read it out? Well, you have to access it first, and that's something that our lab has worked on. And our lab in 2021 published a paper where we invented a way of accessing data in a random manner, using Boolean search, which is equivalent to the way we type in orange cat or orange and cat, and we get pictures of an orange cat, right? And if we instead only typed orange, or if we did orange or cat, we would get very different images, right? So the way we did that was to take the DNA data and encapsulate it in little packets that are microscopic, and then barcode them with additional little DNA labels to tell us what's inside of those files and be able to search through them. You have to read it out, and that's the sequencing it. So you take the polymer and you sequence it. And in this case, we're sequencing the DNA to read out the digital information from the file instead of reading out the diagnostic state of a gene of a patient or a person.
Yeah, that's incredible. But again, there are echoes of the past about it. Slowly punching out a literal physical string of data, which you then have to make searchable, is a problem which has been around for hundreds of years. Here's Colin.
So if you take the idea of a music box with either studs or holes drilled into a disc, and you turn that into either a long strip of tape, or you turn that into a series of cards, like a single piece of paper, you can represent, in the case of paper tape, a single character per stripe across the tape, or a single string of characters, like a sentence worth of information across a punch card. But each one of those stripes represents a different value in this very physical punched format, okay? And then you can have an arbitrarily long set of data in a roll of paper tape. And indeed, yes, you have entire rooms dedicated to this, because if you can imagine 2,000 punch cards is a stack, about half a meter long. We have copies of paper tapes and punch cards in the museum collection that are well over 70 or 80 years old. And they, because it's paper actually lasts pretty well, but it's not read-write. Every time you want to write a change, you have to write the whole thing again.
Of course, we can't really claim that this is history repeating itself yet again, because in fact, DNA has been around for a pretty long time. Even if the idea of making our own to produce pictures of cats is novel. Here's Mark.
I was actually looking up the history, and Basile Bouchon was a pioneer who actually invented the punch card in 1725. So that's been around for hundreds of years already. But I think DNA has been around even longer. And so that's a huge benefit, is the longevity of DNA. Up until a few years ago, the oldest DNA that was discovered was, in an old horse leg bone from 500 to 700,000 years old. And then more recently, a kind of mammoth in Siberia was discovered, and DNA there was preserved that was 1.6 million years old. So that's a lot longer than a magnetic disk is going to stick around, or a flash drive. We're talking about a long time that DNA can stick around if it's under the right conditions. If you read between the lines, once you write DNA, even though it's costly to make, once you make it, it doesn't require any energy to maintain it. These other media you have to copy and replace every 5 years or every 10 years or whatever it is, which is energy consumption as well, or energy hungry as well. Now, we probably don't need data to stick around that long, but it'll stick around forever once it's made.
Well, what a journey we've been on in this episode. Billions of years into the past and decades into the future. So, what are the next steps for our guests today? What challenges are they looking to take on next to tackle our ever-increasing desire for more power, more space, and less money? For Patrick Osborne, on the enterprise side of things, it's all about scaling.
Even if you think about some of the things that are going on in AI and machine learning, right? The amount of change going on the GPU side, the compute side, really affects data and data management. So I think some of the big storage and media challenges that we're facing right now is designing systems that are going to scale with a certain number of constraints. Right, so power and cooling, right, is always a challenge for customers. Sustainability, right, for customers, making sure that they are providing a sustainable infrastructure for their application developers, and then they're managing that, all the upstream providers. So I'd say when we design systems in mind for customers, it's all around scale, but also, there's a lot of requirements now around efficiency, right, and so that's always a battle. We're probably going to see a breakthrough in new media types in the next few years. I do think that with the advent of low-cost GPUs, co-locating your storage and your compute and GPUs together is going to be something that's going to happen. Yeah. So you think about the democratization of AI, the democratization of GPU technology and things like that. So I think that's going to be an area that it's pretty exciting to see.
For Aidong, it's about embracing the technologies that are right around the corner and keeping a close eye on some of those that are a little further out.
I've just been talking to some professor in university regarding to their latest the quantum memory development. So that's again a trend that we watch for. And one of the things that we're looking at is a brain-inspired technology called neuromorphic, for example. And again, neuromorphic computing is depending on memory technologies. So again, I'm talking about earlier on that there's a phase-changing memory. They are the good candidate for neuromorphic computing.
Meanwhile, Mark is pragmatic about the commercial viability of DNA storage in the near future, but is confident it'll be a technology that lasts.
For us to reach the level of practicality of a flash drive, it's going to be decades. So we need that cost to come down 5 to 6 orders of magnitude before it really becomes something that is viable from a cost perspective. And then also it has to get much, much faster. Writing a megabyte file now can take many days to a week, which is totally not viable, of course, for a practical technology. I think with DNA data storage, I think we're further ahead in the sense that we have a lot of tools and technologies around writing and reading and accessing already. It'll be a decade before there's a practical device maybe that is used for archival storage, like you said, making not just a cloud, but a glacier, which is kind of storing everything that's in every cloud and many orders of magnitude beyond that. But then a practical sort of handheld device, I think that's a little further off. So we'll have to wait and see. One thing I can assure you is it's not going away.
It definitely isn't. You've been listening to Technology Untangled. We've been your hosts, Michael Bird and Aubrey Lovell, and huge thanks to Patrick Osborne, Aidong Xu, Colin Abe, and Mark Batcher.
You can find more information on today's episode in the show notes. Do subscribe on your podcast app of choice so you don't miss out, and to check out the last 3 series. This episode was produced by Sam Dattapoolan with production support from Harry Morton, Zoe Anderson, Al Booth, Alicia Kempson, Alison Paisley, Alyssa Mitri, Camilla Patel, Alex Podmore, and Chloe Sewell.
Our social editorial team is Rebecca Wissinger, Judy Ann Goldman, Katie Guarino, and our social media designers are Alejandra Garcia, Carlos Alberto Suarez, and Ambar Maldonado. Technology Untangled is a Lower Street production for Hewlett Packard Enterprise.